Welcome, students. We are going to be talking about percent composition, which is a useful tool to determine the value and the presence of one substance within an entire compound. Now, so what we're going to do is use this formula, which is going to go over the part that we care about, comparing it to the entire substance, and it's going to generate a percentage for us to have. It's very useful for determining value, whether we want to mine or refine something. So here we go. So using this formula, we take a look at C10H22O12. This is a complex sugar of some kind. Okay, now first off, we need the mass of carbon. According to the periodic table, carbon weighs 12.01. Now in this case, we have 10 carbons. We get this 10 carbons because the problem sits there and tells us there's 10 carbons. So we're going to multiply the 12.01 by 10, and we're going to find that we have 120.1 grams of carbon in this thing. So that's our part of carbon. Now we still need the parts of everything, so we're going to continue on. For hydrogen here, we've got hydrogen, according to the periodic table, weighs 1.01. We're going to times that by our 22 that the problem gives us, and the problem is telling us we have 22 of those. And that means our total mass of hydrogen is going to be 22.22. Okay, then we're going to take care of oxygen. Our third piece to this compound here is there are three. Now, for oxygen, we're going to see that the periodic table says that oxygen weighs 16. I mean, it actually says like 15.99, but that it's like 15.99999 forever. So we're just going to deal with that as 16. And it's times 12 because we have 12 of them. Again, that 12 comes from the problem. Okay, when we multiply that together, 16 times 12, we get 192. Now, normally when I do these problems, I don't write the math out here. I just write the answers to each piece. But because this is the first time that you may be seeing this, I figured it would be nice to go over each piece here. Now, we're going to need to find the total mass of this. And to do that, we're just going to add these things together. So we're going to add that and together. And what that's going to do is that is going to get us the molar mass. The molar mass is also known as the whole, or the total mass, either or. Okay, when we do that, we have that the molar mass is equal to 334.32. So I'm going to write that down there so that I've got it for later. So 334.32. Now, molar mass is typically in these units of grams per mole, but it really doesn't matter too much because we're just going to set it to grams when we're all said and done. So we're just going to sit there and set this to grams. Now, so this is our whole thing. So our whole thing is 334.32, and again, we're setting it to grams. Now, what we're dealing with then is we're going to grab the carbon, since we're looking for the percent of carbon. So even though that is my whole, I'm going to use that with my 12.01 grams of carbon. Times that by 100. Remember, in this case, percentage is just a unit. So as I sit there and take 120.1, divide by 334.32, times that by 100, I get my answer to 3592. 35.92. Now I am going to 2 decimal places because the periodic table I'm using has everything to 2 decimal places. So that's why I'm going to be setting this. Otherwise, the problem will tell you what it is. So you really have to look at the problem, and when in doubt, then you're at 2 decimal places based off of the table that we are using. If you're using a different table, most teachers will accept 2 decimal places anyway, but you should definitely check with your teacher. Now over here, I've got my 22.22 grams of hydrogen, and that's going to be over my whole. Again, my whole is still 334.32 grams. I'm going to times that by 100%. and I'm going to get my answer here. So when that is all said and done, I wind up with a total of 6.65, because it rounds up, and that would be 6.65%. All right, and then I'm going to do this again for my oxygen. So, you'll see that since I'm trying to find all three pieces, it's a little heftier. Now, to be honest, in most like real world applications, you're only really going to care about one piece. And so that's the piece you're going to put on top. In this case, we care about finding the percentages for each of these three things. That does happen every now and then, although I have found that it is mostly something that occurs in the realm of science classrooms and less in the realm of things like laboratories or whatnot. And here you're going to get 57.43. Now, sig digged and all correct, this should add up to be 100. If it doesn't add up to be 100, that happens sometimes. It just has to do with, your rounding. Now, what I wrote, you may not have been able to see because my smiling face may have gotten in the way. So just to show it up here, so that way, you can see it. There is my part for oxygen. Here is my whole thing for the compound. I'm timesing this by 100%, and it equals the number that is set right there. So that's how you do with a rather basic, rather standard percent composition question. Now, our next hurdle is parentheses. As you see these parentheses here, this is aluminum nitrate, it turns out. We're going to be learning more about polyatomics as time goes on. But what we really need to deal with is we need to deal with the fact that this is a distributing question. So this 3 that is here, right? This 3 subscript that's outside the parenthesis, this 3 is going to affect both the nitrogen, it's also going to affect the oxygen, and this 3 is also affecting the oxygen. So, you've got 3 of 3, so you're basically going to be multiplying it, and you are distributing it. So if you remember your algebra, then that should be good. Other than that, it's fairly same to the problem we just did with the added hurdle of distributing. So first off, we've got our aluminum. Now our aluminum is alone, so it's just 26.98. Then I've got my nitrogen. Now remember, normally I don't draw the various maths here. I do the math in my calculator and I just draw the answer. So I'm not going to do that. I'm going to just draw the answer. So here we've got 3 nitrogens, and each nitrogen is 14.01 by the periodic table. So if I times that by 3, I find out that my mass for nitrogen is going to be 42.03. All right, so I'm going to have that down there, and that again is my nitrogen. And then I'm going to take care of my oxygen. Now my oxygen there's 9 of them. As you see here, you've got 3 oxygens that's next to it, 3 oxygens that get distributed. So in the end, there's going to be 9 oxygens. So, 9 times 16 leaves us with 144. You'll notice that in a lot of these questions, oxygen takes up an awful lot of mass because, that's just kind of how it is in real life too. Oxygen makes up an awful lot of what's around us. Okay, now what we're going to do here is like we did before, we're going to add these together to get the whole. So we're going to add those, and that should give us our, our total mass. All right. Now, so it's 26.98 plus 42.03 plus 144 equals, and we find that this is 213.01. And we're just going to set that to grams because, again, all we care about is the grams. Normally, molar mass is grams per mole, but we'll get to that later. All right, so in this case, we are set to do what we did before. We're just going to find each piece as we go, and when we do, we're going to get our answer here. Now, I know you're all really tempted to watch me do that, but I'm not going to. Instead, I'm just going to reveal the answer for you, so that way you have an idea. As you can see here, you have got the aluminum here. You've got the 26.98 grams over the 213.01 grams, which was the molar mass or the mass of the total. And again, you find out that that is 12.67. And if you continue to do the same thing, you've got each piece. And again, notice oxygen takes a lot, and we are distributing. So that's kind of the goal there. Now, that's what happens when we have parentheses. Our next hurdle is a slightly different question. In this case, we've got 3 different compounds of lithium, and we want to know which one's the best for mining lithium. So we're still going to use our equation here, but instead of finding the pieces for each of these, all we care about is lithium. So the focus is going to be on lithium. And if I check my periodic table, I find that lithium by itself weighs 6.94. And as you see here, so I've got my 1 lithium here, so that's 6.94. And I've got my chlorine over there, which is 35.45. And so the part that I want, there's only 1 lithium, so that's 6.94 grams of lithium over the whole thing. So I've got my 6.94 plus 35.45. And that equals my 42.39. And that's grams times 100%. Again, the percent is just a unit. And as I sit there and solve that, this will give me my percentage of lithium in this compound of lithium chloride, what it turns out to be. And we find that in this case, we are at 16.37%. Okay, so there we go. That's how much there. But I want to know the lithium and all the other ones. Now you might sit there and be like, hey, this next one has got 2 lithiums, so won't it be twice as much? No, that'd be way too easy. That'd be like lovely, but no, that's not how it works. What we need to do is we need to do the same steps we've been doing. We take the 6.94, we times it by 2, and we find out the mass of lithium here is 13.88. Okay, then we've got our carbon of 12.01, our 5 hydrogens of 5.05, and our 2 oxygens of 32. When you do this enough, that math becomes pretty quick. We add it all together because that is how we roll. That is what we want. We want the total mass. And in which case we find that the total mass of this compound is 62.94 grams. Out of that, only 13.88 grams is lithium. I'm going to times that by 100%, and I will get my answer. So 13.88 divided by my whole of 62.94 times 100% gives me 22.5%. Okay, so what we, oh, sorry, 0.05%. So we already know now that the blue compound has more lithium than the red compound, but notice it's not like a doubling. Even though we had 2 lithium ions per compound in the in the second one, we still didn't get it to be just double. So if we look at this third one, which has got 3 lithiums, I mean, that might be pretty, thinking, hey, 2 lithiums did so well, 3 might do even better. Let's find out, because arsenic can be a heavy element here. So when we're talking about our compounds, this is 20.82 grams of lithium for our grams of arsenic, which is 74.92. So we already know that we've got 20.82 grams of lithium. And we're going to add that to our 74.92 arsenic, which is going to give us a grand total of 95.74. And we're going to times that by 100 like we've been doing. And we'll see. So let's find out if this is more lithium than the ones before it. And as we find out, the answer to that, quite frankly, is no. It's 21.75 with rounding percent. So as you can see, the blue one is the best. But just because you have all that work there, which you do need, you do need to show your work in most of these problems, we still need to signify that this one's the best. So I recommend circling the whole bloody thing and like putting a star by it or writing the words best. So in the end, our middle ore was indeed the best for mining lithium. Okay, now, when we have the amount of sample, we're going to actually wind up changing our formula a little bit. Because what we want is we have this amount here, and that's going to be more important than the percentage. So what you should do is you should literally just replace the 100% with whatever your amount is and base your sig digs off of that. So in this case, we're dealing with calcium in 50.0 grams of calcium carbonate. Turns out that's what that is. So we're going to do what we've been doing. Calcium is 40.8, so 40.08. Carbon is 12.01, and 3 oxygens is 48. Now again, all we care about is the carbon. So all we care, or sorry, the calcium. We don't care about the carbon, we care about the calcium. Be careful about that. So 40.08 grams of calcium. Now we need the whole thing here, so that means I need to, do some math. 40.8 plus 12.01 plus 48 equals, and we are at 100.09 is our total here. So 100.09 grams. Now, instead of timesing it by 100, I'm not going to do that. I'm going to times this by 50. And the reason I'm doing that is right here. It comes from the problem. The problem is telling us this is 50, and not only that, it's 50 grams. This helps us save a lot of time, and so we should totally do it this way. It is way more handy. And I have to admit, it was a student who actually went over this with me. My college professors taught me the long way. This is the short way. You should use the short way. Okay, being that we have 3 sig digs, we're going to need to sit here and take our number. I'll just write a couple digits out there. And this is way too many. We've got 3 sig digs from the problem. So 1, 2, 3. The 2 does not round up the 0, so in the end all of this falls off, and we are left with our answer of 20.0 grams of calcium is in that sample. So there we go. Okay, so this here is the extent that academic chemistry goes. Now, if you're in an honors class, there's another hurdle, and that hurdle is the mass of a polyatomic ion. Now, when we deal with the mass of a polyatomic ion, what we are dealing with is we're dealing with this. This here is called a sulfate ion. And what we want to do is this here is going to become our gram of the part. So when it's all said and done, this here is our gram of the part. So gram of the part is sulfate, and sulfate means this. And this 3 is going to affect it. Okay, and this is a sample. So we have this thing here, which has got 4 sig digs, and this is going to wind up replacing what was above there, which is just 1. In the end, it's not like super hard, and I'm thinking most of my academic kids could get it, but it's not really required, so I'm not going to worry about it. Now, so what you've got here is basically this. Okay, the sulfate is the 2 pieces, the sulfur and the oxygen. So the sulfur piece weighs 90.18 grams. The oxygen weighs 192 because we have 12 oxygens. 4 times 3 is 12. So there we go. These are your sulfate weights, so we have to add them together to get the number up top. Then we add all of it together to get the number on the bottom. We times it by the sample size, set it to 4 sig digs. Remember, this 0 is not significant, and we're golden. So this is the extent when it comes to honors. Now, there's another type of question that kind of goes backwards. These are empirical formulas, or determining the formula, as I like to say. And what it is you divide each mass by the molar mass that you get from the periodic table to get basically moles. You then divide each relative amount by the lowest number of moles that you've got. Reconfigure, get the best results, and there is our example here. Now again, this is honors level, so for the purpose of this video, I'm not very concerned about it. There'll be another video that you can watch if you want to see how this is done, especially if you are an honor student. But if you take a look at the example here, basically the carbon has a weight of 12.01 grams off the table. So we take the mass it gives us, divide it by the mass from the table, and we get our relative number of moles. We do this for each piece, for the hydrogens and for the oxygens. And what we are going to get, I'm going to switch to this. So we get the hydrogens, we get the oxygens. Now, out of these, the lowest one of this is the oxygens. You see there's only relatively about 4.156 moles of oxygen there. We're then going to take that number and divide it to each one. This is going to give us a 1 for whatever the lowest was, and then 8, and then 3. And it's you kind of got to like make sure you round it to the whole number. It should be that way. So that's one of the big hurdles, is you got to check that it's a whole number. And if you get like a 1.5 answer, you should just double everything, because it needs to be a whole number. So 1.5 is like a trick, then you need to do that. And if you are given the mass, like if it gives you like, and the whole thing weighs X, you need to adjust it to the X. But again, like I said, this is going to be in another video. And so that is the whole percent composition, with kind of a little preview of determining the formula if you are in honors. If you're an academic, determining the formula is a bonus question, which often will show up as extra credit on a quiz or test. And so with that, I bid you all adieu. I hope that you had a good lesson, that you learned a lot. And if you didn't learn a lot, well, sorry, I did what I could, and hopefully that will be enough. Take care.